Hey guys, Denny here at Partey. I'm answering actually a couple of questions that came up. One is for uh, Eric, you know who you are. So I want you to see where the light's hitting here. It's about 185 whenever I checked it right at the spot here. You can see this is actually the reflection from the window. You can see the greens in here. You can see some of the other things in here, but that's in the reflectivity zone. So if you're watching from the front, you don't pick up on that anywhere near as much. That's where the 42% efficiency comes in. Because what's happening is while you can see light hitting the screen, you're not getting the preponderance of that light. The 100% of that light's just washing across the screen. Now, the second thing that that's Polaris, by the way, with the 1600 lumen Xiaomi. So what I'm going to do now, because this, oops, hold on. So I had the other question was around the, you guys have to excuse me, I'm still in my PJs, I've been working, but is around the deltas. I wanted a visual example. So I'm going to do that for you. If I can find my little pad here. There we go. All right. So make sure this is in the camera frame. And then I'm going to zoom in just a bit. Maybe a little bit more. Get that in the frame. There we go. So, if you looked at a scale of screens from white to black, okay? And let's say Vega kind of sits right here. Vega Plus right here. Polaris right here. Sirius A right here. And Sirius B right here. So you notice there's two quadrants between each one of these. Maybe only one between Sirius B and Sirius A. So here's the way that it works. You have a greater transmission loss, and each one of these basically conforms to a color jump up in darkness, right? This is a smaller jump, but you lose more transmission here. Whereas here, you get a bigger jump and lose less transmission. So while it's not the same, it's not uniform, okay? And that would only increase, it would be probably something like this down here, right? So it greatly reduces as you get darker in the screen. But the beauty that we found was there's a pattern. I mean, pattern is obviously it's reducing, but there's a calculable pattern. So we can predict what the transmission loss would be if we were to, say, put a screen here, somewhere between Polaris and Sirius A. We would be able to tell, or at least pretty accurately predict, what the transmission loss would be here as opposed to here. And that, once you understand the trans loss, okay, you can then identify the reflectivity and diffusion needed. So we can help calculate as we move darker and darker and darker into color. You can understand what you need to do in regards to reflectivity and diffusion. Now, most people are going to think that both of those are going to go up. That's not true. I'm not going to go into what they do, but that's not true. So hopefully that helps explain in a visual. I know for me, visuals always work better. So as you get lighter down the scale, less transmission loss from one jump to another color jump. And you say, well, okay, what about the color jumps? Well, our color jumps are, we here referred to them as bumps, a color bump or a shade bump. Those are done by concentration values. So, for example, let's say this difference here is an eighth concentration. Well, that would make this a quarter concentration, right? That's not the values, but just to say, using a value, you can tell by how many different concentrations or how you need to adjust your concentration of toner, how all of this is going to work out. And it comes out really close. It's not precise, but it comes out really, really close. So hopefully that helps to explain. If you guys have any additional questions, like I said, glad to answer them. Otherwise, you guys take care and we'll talk to you soon. Bye.